This is CS. Nope. C at .3510 L13B. The topic is puzzles. Most puzzles, in the sense of what is the difference between a puzzle and a game? This is an intuitive question. What is the difference between a puzzle and a game?
Puzzle has a solution.
And suppose you phrase the game as a decision problem. So there is a solution to every game. But hold on to that intuition.
I mean, I play puzzles and games. But I guess I would say that the game responds to you in a way that a puzzle doesn't.
What responds to you in the game?
I mean...
Oh, you're talking about like there has to be multiple players that...
Yeah, exactly. Formally, a game is like at least 2 players. So there's 2 people. One makes decisions that you have to then react to. A puzzle, you can really think about it in a formal sense, is a single player game, right? A lot of puzzles, so like the definition of a puzzle is one that is single player, most of the time. Most puzzles are in NP. Why should that be the case?
Because there's always like most puzzles are about finding a solution. So if you have a solution, it's easy to check.
Yeah. The solution is the witness. So most of the time, a puzzle is in NP, right? So for example, SUDOKU has, if you want to try to convince someone that a SUDOKU board was solvable, you just tell them the answer. That is the solution, and that is the witness, right? Most problems have such, most puzzles are in NP for this reason. But, and just to quickly give you the whole tree again, we said for all A in NP, there's a polynomial time reduction from A to 3 sat, no, we said to sat. And then from sat, we went to 3 sat. 3 sat, we went to circuit sat, to independent set, which we went to vertex cover and clique. And then from 3 sat, we also went to subset sum and then knapsack, right? Oh, and we also did 3 coloring. Okay. So I claim we're going to put a few more objects on this chart, on this web of reductions here. We're going to put Mario. Everyone knows what Mario is. Everyone's played Mario. You have the Italian plumber. They made a movie about him. Jack Black was in it, I think. Mario is, in fact, NP hard. Now, it's probably not NP complete for reasons we'll talk about today. But basically, one of the reasons NP completeness is fun, forget algorithms, is just you get to sit around and talk about puzzles all day, right? You're just, you know, when you hang out with the old people who play mahjong and smoke cigarettes, it's the same kind of stuff. You just kind of, it's recreational. It's totally, like, sure, there's an implication here about, like, this proves that the best algorithm for such a problem must be exponential time. But, I mean, it's also fun. So most of these problems, and so there's a guy named Eric Demain, and Eric Demain has like 10,000 papers or something, and all of his papers are some form of like this contrived puzzle problem is NP complete, or some version of hardness. There are other notions of hardness that he shows them for, right? He has a paper, and this is like a really big deal because it was really funny, but he has a paper showing many classic SNES games are in fact NP hard. And the famous example he gives is Mario, but he's proven tons of things. Certain origami folding puzzles, Rubik's Cube puzzles, all these kinds of things end up being NP hard. And there's 10,000 results of this form. And anything interesting you could ask yourself about is going to be NP hard. Subproblems in Settlers of Catan and so on. A surprising amount of rich puzzles. There exists a lot of rich theory in how hard puzzles are, in the sense that it's not really a puzzle, right? If it is this hard. Right. So let's just talk about the Mario reduction. So first off, we need to frame Mario as a decision problem. How ought we to do that? A decision problem, again, is a yes or no question. What is the best way to phrase, this is an open-ended question. What is the best way to phrase the video game Mario as a decision problem?
Can this set of inputs beat Mario, reach the credits?
So what is the problem? Yes. The problem is, but what should the input be? Right? Recall a coloring problem takes as input graphs and should output a coloring. What should the input be? Yeah. So the button press inputs won't be, I would not consider to be the problem. I would consider that to be a solution.
They're saying that's the witness.
Oh, the witness.
Yeah, the witness is a set of inputs over time.
So two,
Decide whether it gets you to the flagpole or not.
two problems. First, let's talk about the problem, and then we'll talk about a solution. The first problem is the level. So, level. I don't know. L is solvable. In the sense that there is a path Mario can take to reach the level, the final answer. Or-
The original Mario, more like Mario Maker. Like you're trying to prove.
Well, yeah, for any possible level. Of course, for example, graph coloring in the easy is really easy. Actually, there are AI that beat Mario, right? tasks and things like this. But the reason that works, even though this reduction is going to be correct, and those won't contradict each other, because most of those levels, the real levels, actually just scroll left to right. So in that kind of subcase, in fact, it's really easy to solve Mario. But we're talking about in general, where just any possible level, and it is in fact Mario Maker, right? What were we talking about with the witness?
The witness is the set of inputs that beats it.
Okay, does that work? Let's think for a second. Everything has worked so far. There's no reason, the sun has risen every morning. It should rise tomorrow. But let's double check we know why. Mario is an NP? Question mark.
What is the, are we offloading the effort of running Mario to some other machine that we don't care about?
That has been true for every single NP complete problem. SAT is hard in the sense that a formula is satisfiable if someone else knows the solution to it. It's hard for us to find the solution, but we can still argue about it if it exists. Same thing if there exists a graph coloring, if there exists a vertex cover, if there exists a clique, if there exists an independent set, if there exists a subset of items that sub to a target, if there exists a selection of items that sum below a weight capacity and above a value threshold.
But can you run Mario in polynomial time?
That's what I'm asking. That's part of what I'm asking.
Well, what would it be based on?
I'm asking, what is the verifier if you claim that Mario is an NP? Yes.
Something like abstract, like I beat Mario once, like know how to beat Mario, like that's your weakness, or
So what encoded in the data structure format? Tell me a little bit more. What is the witness?
well, I guess maybe like for a given level, you have like you have to jump, go forward, or
So you could say a witness could be a sequence of button presses. So a witness could be a sequence of button presses that you, question? Yeah?
Why don't we encode it as the path that Mario took as a graph, like a directed graph?
Okay, that could work. Like a literal path, like at each second he's at these time steps.
Yeah.
Okay. The reason I'm asking this in such an open-ended way is that the original paper by Eric Demain could not conclude that Mario was an NP. We don't know. Here's the answer. Let's say the witness is a sequence of button presses, and the sequence of button presses per instruction call or whatever is the witness. And that would tell you if the level's solvable or not. You could do so in linear time in the size of the witness by running through the witness and then just checking like you hit the goal at the end, right? Fine. But this may not be polynomial in the size of the level. It could be the case that the sequence of button presses is unoptimal or something and has some kind of exponential rolling up and around. And you could never determine if the witness, it's not necessarily true that there's always a polynomial time witness, polynomial sized witness. There could be a correct witness that is exponential time in the size of the level. So they couldn't conclusively say Mario is not an NP for this reason. In the terms of the number of, let's forget about literal seconds and let's consider time step. Let's consider like an instruction of the NES emulator to literally be a step.
There's a limit to the amount of steps you can have in a certain time frame. Like you can't.
One step per time frame. Let's say
Yeah,
that.
so-
No, what she's saying is that like a Mario level might have like a 5-minute timer. Like,
Forget that.
Okay.
Nah, I don't care. Everything is solvable in constant time if you only have 5 minutes.
Yeah.
So, anyway, we don't know. But that's okay. We can still prove Mario's NP hard. Where are we going to go from? There's no problem like this, so why not try from 3SAT? Right? So again, we need three things-ish. We need some kind of part that says xi is 1 if and only if not xi is 0. Something like that. We also need to force each variable to be assigned, and each variable must be assigned, and no variable can be both true and false, so they must be exactly 1, right? We also need a clause gadget of some kind. And we need some kind of AND mechanism. So what we're going to do is connect a sequence of tiny levels together, and that's going to be our giant Mario level, okay? So first we describe how to make this x1, this x, for each variable, how to assign it to be 1 or a 0, but not both, and not neither, right? So here's the level. Let's see if I remember this. There's a big hole. Wow. Okay. Something like this. Okay. So what happens is Mario comes to 2 holes, and he has a choice here. He can choose to jump in here, or he can choose to jump in here. Okay. And then there are 2 doors. So we would call this the variable gadget, or the literal gadget, and it looks like this. And note that when he's in one hole, he cannot jump into the other hole, right? So he goes to one hole, and he can ground pound on these blocks, and these blocks have mushrooms in them that will connect to other things we'll say later. Okay? But each of those has a little staircase that sends a mushroom somewhere else, okay? So whichever hole he jumps into, this one corresponds to x1, this one corresponds to, let's say, not x1. These will then be, quote unquote, wired up by a path for that mushroom somewhere else, okay? First of all, can he choose both? No. Now we need to make him choose one, because we're going to put a little door here on both of them. And the little door is going to connect to the next clause gadget. He can't ever go backwards either. So this, we could just say, is a teleporter to the next variable gadget, to the next variable gadget, to the next variable gadget, right? So if I were to show you what the beginning Mario level looks like, we do one of these for each level. So here he goes into the first one, and then we wire these up appropriately. Something like this, right? So would you agree that at least if we have n sublevels like this, that he has to, in order to get to that last one, he has to go through the first n minus 1 of them, okay? So he chooses an assignment. We've done really the hard part. Mario now has to choose, by choosing a path through which doors he takes here, he has to choose an assignment, right? So now we need some kind of, any questions on this variable gadget, right? He must choose one of x or x naught for each one. Not both, not neither, right? So now we need something like a clause gadget. And then we need to somehow make every clause satisfied. But a clause is satisfied if any literal in it is satisfied, right? It could be satisfied in more than one way. So what we're going to do is send these mushrooms to different rooms such that the room is only solvable if Mario has a mushroom. So if we sent a mushroom there, then he can solve it. We'll just do this for each room. It's going to look like this. There's some vents here. These are really like stepped stairs, right? Whatever. Mario enters the room. And then he goes through this room. It's boring. And then there's like the fire thing here. I don't remember. And Mario has 2 modes. He has little Mario mode and then big Mario mode. So if the mushroom falls into the room, Mario can go from little Mario to big Mario, right? And by going from little to big, he can tank 1 hit and then go through the fire. Do we agree that this room can only be passed if there was a mushroom in the room? Okay. Now we're also going to take the rule that Mario eating 2 mushrooms does nothing. It's fine. A clause can be satisfied in more than one way. Do we agree that this clause gadget can be satisfied if and only if there is a mushroom in the room? So, and this will be important for the reduction later, if there is no mushroom in the room, that clause gadget can never be satisfied. Okay. So how are we going to wire these up? We're going to make for each clause such a gadget. And then after he chooses assignments to the variables, he gets to walk down this path and enter the first clause gadget, the second clause gadget, and so on. And again, these are all wired up mushroom-wise to send mushrooms to specific paths.
So jumping into each hole makes one of the ones it's connected to solvable.
Exactly. Every time you make a choice, and this is true for SAT, every time you make a variable choice, if you set a variable to be true, certain clauses are satisfied, but you've also perhaps prevented yourself from satisfying other clauses that may contain not x. If you set x to be 1, not x is 0. So that clause has to be satisfied in some other way, right? Recall, like, if you have a or x or b, and c or x naught or d, then if you choose x to be 1, that implies that c or d must be chosen, right? So you must choose to satisfy, if you choose, not only is choosing x1 to be 1 satisfying some clauses, but it forces you to find other ways to satisfy other clauses. So by actively choosing to go down one hole or the other, you prevent yourself from doing the other hole, right? It's not simply just choosing a hole, but also not choosing a hole. That's also important. Anyway, we wire up the gadgets like this, and then at the end of this nth gadget, or k, if k is the number of clauses, we have our little goal thing, right? There's a small problem here, technical detail. It's not super important, but in the spirit of reductions, it is. There's a problem. This is like, if you've played Mario, this is something you would.
Can't Mario get hit by the fire but then not continue?
So in the design of the clause gadget, he is little when he enters the room. He eats the mushroom, hits by the fire, so he tanks one hit, but then he leaves the fire small. So he starts the next clause gadget small for each one.
Yeah, I'm saying that isn't it possible for Mario to die even if he has a mushroom?
There are unsatisfying assignments to every CNF. Yes, question?
You go in big, get hit, get invincibility frames, go back for the mushroom, and then go through the fire.
Sorry, you go in big. You can never, as designed though, because you come into a clause gadget small. You can never go into a clause gadget big. That's important. You can only exit a clause gadget to enter the next one by being small, because you need to tank one hit. Okay, the answer I'm looking for is like these. How do these cross? How do you know your wires don't get mixed up? How do you know you're sending something on the right level? Yeah, so two things you could say. One, it's not necessarily true that you can always plan routes such that there is never a crossing. That's not true, actually. In fact, you can construct a CNF that's isomorphic to a graph that must always have a crossing. That can be proven. But two things you can do. One, modify the reduction in such a way that there is like a teleporter or something, if you allow that kind of block to be built. Two, or, and this is kind of a difficult bit of programming that I kind of want to skip, you put a crossover gadget here that is specifically to allow mushrooms to go cross over each other in such a way that they can't get the pipes mixed up. So you can never be like, this one is supposed to go that way, but accidentally makes a turn or something like this. And I could leave it to you as an exercise to figure out how to actually make a cross gadget like this. It's not particularly difficult. It's just a little bit of one-way door magic, and it's this tall, and so on. It's not super complicated, but know that it's a detail that must be mentioned. If you were, depending on which rules of Mario you take, how that would be done. More questions on the reduction itself before we get to the if and only if? Okay. We want to prove, first off, does the reduction take polynomial time?
Yeah.
Why?
Because there's only, the number of clauses is the number of levels on the bottom and the number of variables or section on the top.
Yeah, exactly. Number of variables, number of clauses is at most a polynomial number of wires. So, yeah. Let the level, no. Let phi be in 3 set. Why is the level satisfiable? Then there is a satisfying assignment. Have Mario choose the correct mushrooms to send. He then passes each fire and completes the level. So we know that the level is in Mario. The level is solvable when the formula was satisfiable. Now suppose the formula was unsatisfiable. We'll do it this way. If the formula was unsatisfiable for any assignment, some clause is always unsatisfied. Mario always dies in the corresponding room. So the level is unsolvable. This is sufficient for us to show that there's a polynomial time reduction from 3-sat to Mario. QED. Questions on the reduction? Two things we could say. One, no Mario level actually looks like this, right? So this is not a very practical thing. It's, if you were to restrict yourself to the case of like real Mario levels, they're all solvable because they're just like side-scrolling kind of things, right? And then you just make very local decisions about what's going to happen next. But it turns out that in the most general case, Mario is NP complete. And such, as long as we can find one case that should take exponential time, the whole problem takes exponential time, right? Big O is of the worst case possible things, right? Second thing we could say is, you ever notice on these like websites and things like this that allow you to upload your own level? Mario Maker's one. I think COD Zombies has custom maps, things like this. Sometimes they do or don't check whether or not the level is even beatable or not. But, sorry?
Does Mario Maker force you to only publish levels that you can beat?
I have no idea. I've never actually played Mario Maker. Well, I won't say this is the reason why, but they don't. Let's suppose you were trying to design a system that could automatically check whether or not the level was solvable without having the user beat it for you. This is the Mario Maker upload system has two different complexities for this reason. By saying you solve the level and show us the answer, they're asking you for the witness, quote unquote. We don't know the witness is always polynomial size, but they're asking you for the witness that they simply have to verify. That's a much easier problem for them than to actually try to solve the level, because such a level like this must take at least exponentially, under other complexity assumptions, must take at least exponentially many tries to solve a level, right? So if Mario Maker were to offer as a service, we'll check if your Mario level is solvable for you. You say, great, I can use you as a service to solve SAT formulas for me. So this is why systems like that require you to submit the solution if the level is beatable, rather than having them figure it out for you, among other reasons, right? Question?
I mean, do such checkers need to be like efficient? I mean, what if they have an exponential time algorithm? Do they care about it? Or?
Well, what this really says is the best algorithm must be exponential time. We can't prove that, but under all these other conditions, that must be the case, right? Now, of course, you can restrict Mario to be something simple, and then you don't have any problem like this. If there's a finite number of blocks, if all kinds of other things that are in the problem description, then that changes the answer significantly. But in this special case of general-sized levels, these specific blocks, this specific behavior, Mario's NP hard, only under those conditions. You change the conditions, you change the problem. Questions on Mario? Let's do 2 other quick games. So the other game is Sudoku. There's a few other games I thought about showing, like RNP. I'll leave that up here. RNP, NP complete or NP hard. Wordle is NP hard. Minesweeper is also NP hard, but these reductions are quite cumbersome. So I wanted to choose one that was rather simple. So does everyone know how to play Sudoku? Okay. So Sudoku is you have the 9x9 board, right? And then you must fill each square with numbers 1 through 9. Each row must also be filled with numbers 1 through 9, and each row and column must also be filled with 1 through 9. And the board is given as an initial, some cells are filled for you already. By the way, I don't know if you ever tried this, but a random board has a pretty high likelihood to be unsolvable, right? You can always construct boards that are not solvable. For example, suppose we did this. Right? Some initial configuration of a board is sometimes not solvable. There is no way to solve such a board, right? Another thing is, like, this is not true for Mario, but it's true for Sudoku. Sudoku is a finite game in the sense that there's only finitely many boards. It's a large number, but in some sense, you could say Sudoku, being a finite game, can be solved in constant time, where you have one program with a quadrillion if statements that just checks it and has hard-coded the answers. Chess, in this sense, is also a finite game, but this doesn't make any sense because the number of valid positions is greater than the number of atoms in the universe. So you could never even write down such a program, but it exists in principle. So up to the way we measure runtime of algorithms, though, that technically counts. So that would be a constant time algorithm for such a thing. So we don't do that. Instead, what we do is we have to parameterize a some function of n that increases. So we can say it's linear or it's growing or something. So the way we'll define Sudoku is to be boards B such that B is a 3n by 3n board. Sum filled and is solvable. So there is a solution to such a board, okay? This is the formal version of Sudoku. Sudoku is in NP. Why? And also n by n board. And what do we mean by filling it in? Symbols, let's say, the answer would fill in symbols 1 to n. So instead of 1 to 9, it would be 1 to n. It wouldn't be like 10 or 11, it would be like an emoji and a letter and so on, things like this, right? Whatever those symbols are. Why is Sudoku in NP? Sudoku.
You check every column at the witness.
So first off, what is the witness?
A filled board.
Describe a little bit more detail, data structure-wise.
It's just a n by n grid completely filled out.
Yeah. Okay. Right. Let's just say that. You just plug and chug and you check that there is no inconsistency. Why does this take polynomial time? If you have a 3n by 3n board, each square touches a row of size 3n, a column of size 3n, and a square of size n squared. So that's polynomial, right? So what is that going to check? It's going to check 3n plus n squared cells and check that there is for each square. So, and how many of those are there? Right. So, don't know what that is, but it's polynomial. There's probably an easy way to do it, but it's good enough. right? Just check all those squares. Consistency can be determined in such a way. Okay. I claim Sudoku is NP hard. What problem on this chart of problems should we want to reduce from? Okay, 3-sat is one option. Yeah, that's, well,
I think N color.
that's why I did N coloring. Sudoku. I claim we can perform a reduction from N coloring to Sudoku. Because N coloring is hard, so must be Sudoku. Why? What's the argument? Sudoku? Okay. Sudoku?
I think it's Sudoku.
Sudoku, okay.
A lot of people say Sudoku. but
Sudoku?
it's-
Sudoku? Is that, what?
That is correct.
Okay, I don't know, which one?
What you have
What
written is correct.
Sudoku. Okay, Sudoku, thank you. Okay, okay. What's the reduction from N coloring to Sudoku?
You just put a line between all the ones in the same row and then all the ones in the same column. And then
It's-
all the ones in the same box.
It's actually a little more complex, but basically. So what you're going to do first is you convert a 3n by 3n table into a graph. And the graph is going to, let's just do the 3 by 3, for example. Okay. Each cell gets a node. You want there, you know that if a cell is a certain color, that none of the other cells that it is related to can be the same color, right? Let the color be the number. So here, let's suppose we're considering the 9 coloring problem. We know that this vertex must be connected to those, so it's different than all of those. And in fact, something stronger, all of those are connected to each other. It is a clique of size 9, but let's just focus on one cell so I can draw the picture. Let's focus on this guy. Nope. Let's focus on this guy, okay? So it's connected to those 3, those 2, those 8, but then it must also be connected to those 2. Okay, and then you must do that for every vertex. For every vertex, right? This is not done yet. This just simply is the association between vertices and which one they are related to. A Sudoku board is a nice thing you can fill out, but is really a really ugly graph with lots of edges that are implicitly there, right? We'll count the number of edges in a second, but this is not done. The board is partially filled for us. By the way, does anyone know in the 9 by 9 case what's the minimum number of squares that must be filled to guarantee if there is a solution it is unique?
It's like 17 or something.
I thought it was 14 or 15, but I could believe 17. For example, if there's a square with one cell filled in, it's easy to solve. It just, what is it? Backtracking is really, it'll do it quickly. But how can we make sure that certain cells begin with the same quote-unquote color?
You connect them to, you
Let's take a second.
immediate cell of every single color in between them.
But a board may have more than one solution. Sometimes they may be the same color, and sometimes they may not be. This is a tough answer. Question? Yeah?
Connected to every other thing that isn't the same as it, doesn't start as the same number as it.
Basically. It's more complicated than that, but you create this other thing, which is a clique of size n. Let's do 4 here. And let's say you want this one to be colored 4. You connect it to 1, 2, and 3. leave that under the board somewhere, and then have everything but 4 connect to that one, right? By the way, coloring Sudoku, same thing, because if there's a permutation of the colors, there's a permutation of the answers as well. It doesn't really matter. But the board would be instantaneous in some way, the same way, right? We need to just ensure this is polynomial time, because there's actually a lot of edges here, right? So there are, how many squares are there? There are 3n squared vertices. Each one, let's say it takes unit time to draw an edge, to connect an edge. We are taking as input a graph. I did the reduction backwards. We're actually reducing from Sudoku to N coloring.
Yeah, we gotta go the other way.
The reduction is backwards. This reduction does not show, okay, this reduction does not show the hardness of this. I'm just going to finish the reduction anyway, but it doesn't show the hardness. Okay, how many possible vertices does every vertex connect to? Suppose in the n case, in the 3n by 3n board. So it connects to n squared minus 1, right? How many are in each row? 2n, 2n. Forget these because we already did those, right? So let's get 2n, 2n. Okay, there are a lot of edges.
It's only 2n.
Column, right?
Oh, yeah, yeah.
Right? So there are whatever that is, it's a polynomial. There's a polynomial number of edges that must be written down on the first gadget. What about this other gadget here? There is a clique of size n, and then for each one, you have to connect n minus 1 wires to up to 3n squared nodes. That's also going to be a polynomial, whatever it is, right? You have an n by n clique, and then you have n minus 1 wires per possible 3n squared vertices. That has to be done. So that's just going to also be polynomial. You sum all that, there's at most a polynomial number of edges. Done. Does the reduction take polynomial time? Yes, because there's a polynomial number of edges to write down. Following this way, it can be done easily, right? Unfortunately, I got the thing completely backwards. It goes from Sudoku to N coloring instead of vice versa. So if someone claims that they can solve N coloring for you efficiently, then they can solve a Sudoku board for you. The reduction as written here takes a board B, and it outputs a graph, a 3n by 3n board, partially solved, and outputs a funny-looking graph and this number n, right? Unfortunately, that's the wrong way. So this doesn't actually prove Sudoku is hard, so I don't get to say anything else about that. Oops. Any questions? Okay. I'll do one more for you. Everyone likes little triomino games. Suppose that you have two things. One, you have an open board. You have a set of pieces. And you have a board of the following. Board of the following. Where the board is some kind of grid made out of wood with open spots in it. And the pieces are all just glued together unit squares. So maybe they look like this. Right? Just all kinds of the Tetris pieces for whatever combination they could be. No bound on the size or anything. whatever, right? Some pieces like this, and you have some kind of open season field. Suppose in the simple case your board is a rectangle of a certain size, and you want to know, given only a certain number of pieces, is there a way to plug those pieces in such that the whole board is covered, right? A lot of games have a mini game that looks like this, right? Talos Principle is one. I think there's probably a million of them, right? But can you make, you don't have infinitely many copies of each piece. You have only these pieces. Can you take these pieces and overlay them in such a way such that it covers all the required squares and none of them overlap, right? Have we all played a game like this or seen a game like this in some way? Okay. I claim the problem is NP complete. Why is it an NP? What should we call this? I didn't think of a name for this. Yeah, let's call it puzzle.
Given an arrangement, you can check and polytime if it fills the whole board.
Right. With every such problem, you should always design the witness. Witness should be, let's see, this is pieces. Witness would be what?
Filled board.
Filled board, yeah. Some data structure decisions need to be made there on how that is. It's a little complicated. Determine like this goes there, this piece was here, I didn't use this piece goes there. That's a polynomial size answer, right? The answer is polynomial size. So it can be done in polynomial time, right? Questions on that? Kind of a hand wave on that one, but we perhaps believe it without filling in the details. Someone could tell you how to fill it in. NP. It's all really NP really is. I claim the problem is NP hard. What problem should we reduce from? And this is basically the whole point of this.
Feels like a constraint.
Why?
Because you have you can call a board like the capacity.
So which problem should we reduce from? Pick one.
The DP one.
They both have DP solutions, in fact.
What is that? What does that stand
Subset sum.
It feels like that.
Yeah, sum to a target T, right? Remember we did a whole lecture on that?
That's like knapsack but constrained where you have to get the exact answer.
Yeah.
Okay.
Right, coming back to you.
Subset sum then.
Yeah.
Okay, what's the reduction? That's correct. We're going to reduce pos from subset sum.
I guess the board is the target.
So what is the, great question. Let's figure it out. Subset sum. We reduce from subset sum to this puz game. Let me make sure I'm doing it the right direction. Yes, okay. What's the reduction? We have, in subset sum, again, a set of items and an integer value t, and we want to map that to pieces and a board. What is the actual reduction?
Can you sort of chunk up the puzzle into blocks?
You can do whatever you want in the reduction. It only needs to preserve correctness. And this is the spirit of these exercises. How did we go from 3 coloring to n coloring? You went to an extremely special case. Question? No. Okay. You can go to any specific board and any specific set of puzzles, but but you must begin with any set of items in any target T, and have the correctness property that if they sum to the target, then the puzzle has a solution. If they don't sum to the target, then the puzzle has no solution. You have to translate faster than you can solve. And again, it need not be surjective or anything like that. Someone comes up to you and says, I can always solve these puzzles in polynomial time. You say, great, you're going to solve this subset sum for me. That's basically what every reduction is.
Line.
The line? Line?
Long puzzle. Like.
Okay, the reduction takes
in.
okay,
Just
well,
the lengths
is there a word?
of your integers, and the puzzle is just a line t long.
Yeah. Okay. puzzle consists of, for S is an S, let P contain 1 by S piece. For example, if we have the set 2, 3, 5, target 7, unsolvable, but let's just suppose that's what, there's no solution there, but let's just suppose that is what it is. We would have okay. Okay. Can you choose these pieces to fit in here? No, because there's no subset.
Wait, yeah, we can do 5 and 2.
Sorry. And it's important that this definition of puzzle is given in such a way says that there are no blank spaces.
5 and 2.
Oh. No, that works then. So this puzzle is solvable. Sorry, no, I was thinking 8. No, 8 also works. I don't know what I was thinking. So this puzzle... 9. I'm not going to draw that, but it works. It works, right? So anyway, the point is the problem is defined in a really general and really ugly way. It's really horrific. But that's okay because it's a generalization in a very specific way, a generalization of an NP-complete problem. So if someone can solve this horrible and ugly thing for you efficiently, they can solve it in the special case. But the special case, as we assume, is as we know is NP-complete, so we assume takes exponential time. So it doesn't matter how good they have it for all these other inputs. You can find a subcase that takes them exponential time, right? By the way, again, algorithms we measure in worst case analysis. So sometimes solving a problem is easy on average or something, but that's not the question. The question is like worst case, right? So we found a worst case of the problem. Doesn't matter if most of the time it's solvable in an easy sense. This is a subset that takes at least exponential time under certain assumptions to solve. Therefore, the whole problem takes exponential time. I don't think I need to do the reduction, but if I were to say it out loud real quickly, let S, T be in subset sum, so there exists a subset S prime which sums to the target T. Consider the puzzle instance. Consider the exact same set of items that correspond to elements in this subset S prime. Note that when you connect them in any order, they make a segment of exactly length T, which happens to fit exactly in the puzzle. So the puzzle has a solution. That's the if direction. P implies Q direction. When we do the only if direction, suppose that the puzzle is solvable, then a selection of items, therefore, can be conjoined to have a length of exactly T. This corresponds exactly to a subset which would sum to T. So the S, T would also be in subset sum. If and only if done, the puzzle is harder than subset sum. But because they're both in NP, they're as hard as each other. Done. Right? You can imagine that there are more complex and worse reductions as you get. I can leave it to you to Google. There's a reduction, for example, Minesweeper is NP hard, but it involves converting NAND gate circuits into solvable Minesweeper boards, something like this, right? The reductions can get very complicated, so I like to focus on like the simple ones. But note that there's a zoo out there of harder and harder and worse things. Any questions on puzzles? Some puzzles that are NP complete? All right.